Hello and welcome, class. Dr. Bowman here. We are continuing our march through Chapter 1 of Burge and Overby's Chemistry Atoms First. If you didn't watch the first lecture, you don't necessarily have to watch all of these lectures in order to get the meat of what it is that I'm talking about, right? I'm trying to collect these lectures into isolated, cohesive kind of topics. However, if you've never taken chemistry before, it's going to be a good idea to kind of get some context for what this lecture is about, since the study of chemistry is cumulative. So as we continue throughout the semester, we are going to be each new lesson is going to be built up off of the lessons that came before it. Why am I saying that? You might be watching this video out of isolation. You may or may not be from my actual class. Yes, I am a chemistry professor. I am recording these lectures during, as you can see by the timestamp, COVID-19 pandemic, but also for posterity. So this lecture is on the physical and chemical properties of matter. In part 1, we've already defined how to classify matter, what is matter, so if you want that lesson, go back to part 1. Either a link is in the description or the comments down below. I'm not sure exactly how I'm gonna annotate and all of that stuff. I'll figure that out as I go. It's fine. I'm just having fun with this, right? I'm someone who loves chemistry and I want to share that love with everyone around me. So the lectures will be somewhat cumulative, but again, had isolated topics. We have themes as we go. Chapter 1 is all about foundational definitions. In this part 2 of chapter 1, the definitions that we're talking about here, physical and chemical properties. So let's get started. All right, so we've already talked about elements, compounds, homogeneous and heterogeneous mixtures, all of the definitions, how we can represent those pieces of matter, but those aren't the only ways that we can classify and talk about matter. So what we're going to do here again is define physical versus chemical properties. So these are ways that we would expect either elements, compounds, or mixtures to behave. A physical property, by definition, is a property that is measured through physical change. So we're not actually changing what the substance is, but it will be a change, or it will change appearance probably in some way. So for example, before talking about the explicit example below, what we can talk about what this little picture is here, right? There is frost gathering on these leaves. We would represent this chemically by saying, well, water, before it was in the form of frost, was more than likely some type of dew in the air, but as the leaves themselves are getting colder, right, in the fall time, at least up here in the north, what happens is that liquid water in the air starts to condense onto cold objects like these leaves and turns into solid water, right? So this L stands for liquid, S stands for solid, and yes, we can write some type of vague chemical equation for this for this change, but the important part is that we are again not changing the chemical composition. The physical change that happened was the water went from liquid to solid, but it's still water. It's just different in appearance. So this is what we would describe then as a physical property, how easily, at least in this first example, how easily something that is a liquid can either turn into or condense into a solid. Another example of a physical property is one in the example which I will illustrate down below. It is known as miscibility. How easily mixed things can be. Will they separate into a heterogeneous mixture? Will they form a homogeneous mixture? That's what we're measuring when we use the term miscibility. How easily mixed can your mixture be? So if the two things that we are mixing are methane and oxygen, well, methane, we'll say here's our little vessel for methane, which is CH4. We'll just draw a little methane hanging out. 1 carbon, 4 hydrogens. Maybe we'll give it a friend. Another methane, 1 carbon, 4 hydrogens. But the vessel, no matter where we are looking inside of this compartment, all we're gonna find is CH4. The other vessel, which we are going to mix in this methane with, is going to be oxygen, right? Oxygen is O2. Oxygen is a free-roaming element, is almost never just a single oxygen atom. Oftentimes, we find O2 because this is the most stable form of oxygen to be in. All right, so I'm going to draw a couple of oxygens here. The coloring scheme is going to be a little bit different. I'm only working with like red here, so I'm going to draw like a couple of lines. So it's kind of shaded, but it's not like totally filled in like the carbons are over here, so it's kind of somewhere in between. But regardless, we have another vessel that is comprised only of O2 gas. So if we were to connect these two things together and destroy the walls in between, what would happen? Well, one possibility is like, well, methane's combustible, so like we could make fire, but that is not what a physical property is. Fire is a chemical reaction, right? Combustion is a chemical reaction. We are not changing the chemical composition of these substances. So what we would expect to see when observing the miscibility of these two gases, methane and oxygen, is that we're going to see our kind of two methanes floating around inside of this container. Properties of gases state that our gases are like constantly moving around, right? So it's kind of pinging around, ping, ping. Same with these gases over here. They're in constant motion. And so for that reason, we would expect after these things have been mixed, we're going to end up with some methanes interspersed with the oxygens. Nothing is drawn to scale here. Please forgive me. But all of the methanes and our oxygens are going to end up kind of interspersing with each other. No chemical reaction has occurred, but we are going to end up with a physical mixture of oxygen and methane. And the physical property of miscibility, we would say that these two substances are very miscible. All right, I did just mention combustion though, and that's the thing that everyone loves in chemistry, right? Setting things on fire. Fire/combustion/flammability is what is known as a chemical property of matter, right? So physical properties are measured just by physically mixing things, just seeing how the appearances change. Chemical properties, though, this is a property that you can only measure through chemical change. Your substance will change chemical composition, and in this change, what we are signifying is that there is a chemical reaction occurring. So let's say we have this wildfire as an example over here on the right. Combustion is like the quintessential example of some type of like chemical change that is occurring. The chemical property that goes along with this is known as flammability, right? How flammable is your substance? When it comes to something like methane, methane, it is a very combustible gas. It is just constantly observed as being very flammable. So if we think again of our previous example, where we have one vessel of methane kind of hanging out in close quarters with a vessel, this time I'm just gonna have one wall separating, one vessel of oxygen gas. Like before, what we're going to do is hypothetically remove this wall, allow the two molecules to kind of intersperse with each other, or two compounds to intersperse with each other. But in addition, we're going to add a little bit of a spark. If we add a spark, what this is going to do is give us just the amount of input energy we need to start breaking chemical bonds. And as the chemical bonds begin to break, our methane and our oxygen, our CH4s and our O2s are going to completely break down and rearrange and give us something new. Now the product of combustion, particularly if we're mixing CH4 and O2 together, right, kind of classic knowledge of what the products of all combustion reactions are, we're given CO2 and H2O. And so after the course of the chemical reaction, assuming that everything has burned in appropriate proportion, appropriate quantity, we're going to end up with a carbon dioxide over here, where our carbon is bound to these oxygens, and water, which is again this should be an oxygen. Oxygen, I forgot my color coding, forgive me again. So we're gonna end up with a carbon dioxide and a water molecule. Forget this guy right here. All right, so the proper proportions I do not have illustrated. That is a huge caveat. I do not have any type of like balanced chemical reaction or balanced picture. That was not the point of what I was trying to make here. The point is, in a physical like mixture, right, to go backwards, we take one molecule and a second molecule and just kind of put them in close quarters with each other. So on the right, afterwards, we can see, yeah, these two things mixed. They are physically in the presence of one another, and how easy it is to mix them together. That is like the physical property of miscibility. If we do the same thing though and add a little bit of a spark, we are now suddenly observing something very different. We are no longer observing a physical mixture or measuring a physical property, we are measuring a chemical property. And we know this because the products of the mixture are totally different compounds than the ones that we started with. All right, so how easily CH4 and oxygen turn into CO2 and water, that is a measure of the chemical property flammability. All right, so chemical reactions. I did say in our last lecture, and I'm going to reiterate here, we're not really going to be talking about chemical reactions in any certain depth until at least we get to chapter 8 in this lecture series. So if you're here for chemical reactions and that kind of deep dive, move on ahead to chapter 8, which as of you listening to this may or may not be posted, all depending on when you're listening in time. However, for the purposes of this lecture, I do want to kind of get into the basic definitions for what it means to be a chemical reaction, since particularly if you're reading along with the textbook that I'm using, the nomenclature and kind of language for chemical reactions gets thrown around a lot, even though we haven't talked about chemical reactions in any detail yet. So let's just define what it means to be a chemical reaction, since this does pertain to chemical changes, and we will be seeing this type of nomenclature throughout the semester anyway. All right, so a chemical reaction, this is a transformation of one or more substances. So again, we're kind of looking, at least initially, at a mixture of substances. And over the course of them being mixed together, either again, there's a little bit of a spark, or maybe they're just reactive substances to begin with, we will end up with a transformation, again, into some other type of substances. So a chemical reaction is the physical thing. You put two things together, you see what happens, you see what changes. This is the physical, observable reaction. The reason why I want to kind of technically tack on that description for the reaction, or for the definition of a reaction, is because chemical reaction and chemical equation tend to be used interchangeably, but they are technically two different things, right? The chemical reaction is the thing that you're physically doing. The chemical equation is the symbolic representation of it. So a chemical equation is what represents a chemical reaction, right? This itself, words on a page, is not a chemical reaction, but it represents what a chemical reaction is. So it's like the difference, right, between language and what the language is trying to say. It's the abstraction, right? If you read the word dog on a piece of paper, the word dog is not a physical dog, but it linguistically represents what a dog is. That's what a chemical equation does. It's linguistically representing what a chemical reaction is. So in this hypothetical reaction, what the equation down below is representing is exactly what we just drew and talked about. We have methane, CH4, combining with oxygen on what is known as the reactant side of the chemical equation. The reactant side, which is always the left-hand side, at least in this semester 1 of general chemistry, the reactant side is what illustrates the things that are mixing together. These are the things that are going to react. The reaction arrow then dictates that time is passing. The reactants on the left-hand side are before. What is on the right-hand side, these are the products. They are produced after a chemical reaction, or in the process of a chemical reaction, right, has finished. So our products of this combustion are carbon dioxide and water. Now notice that we also have a couple of additional numbers present that are not subscripts in the chemical formulas. These additional numbers are known as coefficients. These coefficients represent how many of each molecule we have inside of the chemical equation. And if our chemical equation is balanced, then all of the atoms on the left-hand side should transform into something else on the right-hand side. Right, so let's double check that. Let's just kind of illustrate, right, all of this together, not just in some generic, it doesn't really matter what the proportions are illustration, but like, we're gonna take 1 methane, and as is our like list of instructions, right, this chemical equation says that in order for this reaction to completely progress, we need 2 of our oxygens. So this 2 again represents how many of the O2s we have. We have 2 O2s. Right, so again, subscripts refer to how many elements we have inside of a molecule. This coefficient out in front represents exactly how many of those molecules we have. Right, so here on the left-hand side, we can see that we have 1 carbon, we have 4 hydrogens, and we have 4 oxygens, totally present across all of the like atoms inside of these molecules. All right, the products then, that are produced over the course of this chemical equation, we have 1 carbon dioxide, so I'm going to draw that carbon. We have 2 oxygens bound to the carbon that is present here, and we have 2 H2Os. So 1 individual H2O, again, we can see there are 2 hydrogens and 1 oxygen. And we don't just have one of these H2Os, we have a second H2O. All right, so we have 1 carbon dioxide and 2 waters. Now, if this equation is actually balanced, what we should see is, again, all of the elements that were present on the left should still be here on the right. They're just in a new form, right? They've made new molecules, they've made new friends. So what we can see is that we do have 1 carbon present inside of the carbon dioxide, right? We have 1C. We have a total of 1, 2, 3, 4 oxygens, because there are 2 oxygens in the carbon dioxide, 1 oxygen in each of the waters. And we also have 1, 2, 3, 4 of our hydrogens across both of the water molecules. So we can see that we started with the same numbers of atoms as what we ended with. This is a complete balanced chemical equation. Everything's been taken care of, everything's been tallied in our inventory, no leftover pieces, nothing was missing. That is the purpose of what the coefficients in our chemical equation or that's what their purpose is. It's to make sure that everything is balanced, that everything is taken into account, that we have the right numbers of each of the molecules that go into and are necessary for the chemical reaction. All right, so having talked about physical properties and chemical properties, we come to another example problem to kind of dissect, decompress, to digest mentally everything that we have talked about so far. So if you are watching this lecture from, like the actual lecture from beginning to end, please pause the video, kind of dissect and think about how would you identify the following actions? Would they be physical or chemical changes? If in the future you would like to return to this example problem, this is going to also be extracted and uploaded as its own separate video, so that way you don't have to scrub through the lecture to find this again in the future. So if you are watching the extracted version of this example problem, hi and hello. Please keep in mind that this follows up from a lecture, so if you would like more context for this example problem, please feel free to find the link to the overall part 2 lecture that this comes from. We're talking about properties of matter in the description/comment section below. All right, so if you are still listening, I am assuming that you have already paused the video and we are ready to continue moving forward and talking about how we would define these processes as either physical changes or chemical changes. And remember, the bottom line is, does the substance over the course of this process change? So if you're looking at a physical change, your substance does not change. I'll say does not change like chemical composition. That's really like the full caveat. Chemical composition. All right, if the process is a chemical change, your substance will change chemical composition. So formulas will change, atoms will move around, etc. All right, so melting. This is our first example. As something melts, by definition, we are going from an object that is a solid and it is turning into a liquid. All right, so S for solid goes into liquid. I wrote the whole word out here. So if something is going from a solid to a liquid, it is like the reverse of the example that we talked about previously when something's going from liquid to solid. So a really good example is just that of water. If we're looking at ice melting into liquid water, the chemical formula for ice and water is the exact same. And because we did not change chemical composition, yes, we changed form, but we didn't change chemical composition, the process of melting is known as a physical change. All right, so we'll draw a little line kind of distinguishing melting from the next example, which is rusting. All right, rusting is a corrosive process, right? The most just classic example of something rusting is iron turning to rust. And so you might ask yourself, what is the chemical composition of rust? Because that really is like a piece of information that's necessary to distinguish or decide whether or not the process of rusting is known or would be like classified as physical or chemical change. Well, the chemical formula of rust, if you were unaware, or if you didn't rely on like past experience or instinct, the chemical formula for rust is different than that of classic iron. It is Fe2O3. The rusting of iron is what is known as an oxidative process. Oxidative in the like classic sense, meaning that we are adding oxygen into the chemical formula of the substance we're working with. So the process of rusting, since we did change the chemical formula, we did change the chemical composition over this process occurring, is going to be defined as a chemical change. Draw a line down the middle. All right, next up, we have drying. This is a strange thing to think about, right? It's not taking a substance and turning it into a liquid or from liquid to solid. Instead, we are taking two things that were mixed together, one thing that was wet. So let's say your skin, this is your skin, and there's just like a bead of water sitting on top of it. So this is H2O. Well, the process of drying is really just separating the water from, in this example, the skin, right? If you want to dry your skin, you remove the water. In doing so, you don't change the chemical composition of your skin, and you also don't change the chemical composition of the water. Either you're drying it by air or you're drying it by towel, but all you're doing is taking the water and separating it from your skin, right? Water's over here now, skin is over here, your skin is nice and dry, smiley face. Well, the process of drying is just separating two things, where one of those two things happens to be a liquid. But the chemical composition of these two things has not changed. They've just been physically separated by space. Because we did not change the chemical composition, the process of drying is known as a physical change. All right, and last but not least, aging. This is a strange process to think about. If we imagine the aging process, right, generally we can, at least when it comes to humans, think about like, oh, you start as a baby, you grow up, you then get old. But where are the chemical formulas in this? Like, is this a process that can be defined as a physical or chemical change? And the answer is yes, because your body is made of matter. It's made of chemicals. Your body, as you start very, let's say, young, you then grow up, you then get old. So here's my older person. They have a cane here. Your body is changing form. And we may not have one cohesive chemical formula that represents the body, but we do have many smaller pieces that do build your body. Right? We have like the cells in our tissues, and the cells can be even further broken down into the atoms that are inside of them, the molecules that are inside of them, things that can be represented like DNA, proteins, etc. And as you get older, your DNA changes. As you get older, your proteins change. Overall, if we're thinking from the chemical perspective, you are changing form over the process of aging. And if we really want to get down to the technical details, the reason why you change physical form is because the molecules inside of you are also fundamentally changing. They're either proportion or the physical construction of them, full stop. And so the process of aging we can define at the most simple level as a chemical change. Right, it's just something strange to think about. You don't normally think of your own body as being made of chemicals. I don't know, maybe you do. I do a lot. But it is, right? You are a physical object. You are a person. You are unique and you are made of matter. Your own chemical signature is separate from everyone else's, but one thing that we all have in common is that we all will still go through the process of aging. All right, so there are two other properties that we can kind of further define in terms of chemical versus physical. So we're gonna keep going with our lecture, keep rocking and rolling. So intensive properties of matter, these are properties that are independent of the amount of substance we're working with. So these are kind of inherent to the chemical itself. So if we're observing, let's say hypothetically, gold has a very signature appearance, right? It looks yellowish. And so from this color, which we would define as an intensive property, right? It's kind of listed down in the defined characteristics below. Color is an intensive property because it doesn't matter how much stuff we're working with. If it's a fleck versus a bar, gold will appear yellowish in color. We can also use these intensive properties to pick out things that are hypothetically not gold. So this chunk of something silver down below, we can conclude this is not gold because it does not have the classic color or appearance of gold. This is probably something like silver or tinfoil or, any of the other number of kind of gray silverish metals that exist. Some other intensive properties include the density of the substance, melting point, hardness. This is not a comprehensive list. There are way more than this. Freezing point's one. The list of intensive properties, though, and basic definition all have that one thing in common, which is that they are independent of the amount of stuff. So again, if you have a fleck of gold versus a bar of gold, the density of both materials will still be the same, right? The ratio of mass to volume. The melting point of the substance would be the same. It may take less time to melt the entire fleck of gold, but the melting point, the temperature at which this little piece versus the big bar begins to melt, will be the same. Hardness, so how rigid versus how malleable a substance is, again, is characteristic to the type of substance you're working with, and it doesn't matter if you're working with a small piece or a large piece. Again, the small piece may be easier to break or bend, but the characteristic hardness will be the same. All right, so the intensive properties, where I have in highlighted in red, you can remember the intensive properties are independent of the amount of substance. That's why I have in kind of present in red. It's not that there's something special about the word in, it's just that this is kind of a little mnemonic that you can use to remember what intensive properties mean. Independent of mass. This is in complete contrast then to the extensive properties that directly depend on the amount of substance. So these are the properties that are measurement tools. Units like mass, volume, pressure, heat capacity, these are all things that depend on the exact amount of stuff we are working with that we use to characterize how much we have. Now, these properties are important, but they are not defining to the piece of substance you're working with. So for instance, mass, we can have 10 grams of gold. We could have 10 grams of water. We could have 10 grams of fish. I don't know, I'm just adding things. The unit of 10 grams is in common to each of these, but the 10 grams does not define what the substance is. It's just a measurement. It's 10 grams. The example of what you're measuring, gold, water, fish, whatever, could be completely unique and totally different. And this is true for all of the extensive properties. Volumes are not necessarily unique to substances, pressures are not unique, heat capacities are not unique, and this is because they are directly dependent on the amount of the substance that you're working with. All right, so how, is there a fun mnemonic for remembering extensive properties versus intensive properties? Well, one way, at least that I use to remember, is that the prefix "ex" in Latin means to go out from, right? So ex means to go out from, just like the extensive properties are outside of the substance, right? It's the substance doesn't matter. The property is defined outside or separate from that. All right, so the important thing again is all of these are measurement tools. It's not to say that they don't matter, it's just to say that they are not dependent on the substance, but they do have meaning to us. And in fact, that is what the entire next lecture is going to be. So tune in for part 3, either if you're gonna go to class the next day, if you're actually in my class, or if you are in quarantine, if I am in quarantine, whatever. Part 3 is going to go through more of the extensive properties of matter, talking more distinctly and explicitly about units and their meaning. So tune in for that. Again, if you have homework, check your homework. Make sure you're being a responsible student. If you have any questions and you're in my class, do not hesitate to email me. If you are in my class or not, feel free to leave a comment here on YouTube. I'm always happy to share the love for chemistry. Otherwise, class is dismissed.